All right, welcome back. This is video 2 on section 9.4 of AP Calculus BC, defining and differentiating vector-valued functions. We're going to pick up right where we left off at the end of the last video, going into this second example, part B, finding the derivative of our vector-valued function here. This one's a little easier than the last one. So the derivative of r of t is r prime of t, which is again going to be a component form vector. Now, since we're written in standard unit vector notation here, I'm going to write my answer in standard unit vector notation. So we're going to go ahead and take the derivative of the component with I. Derivative of sine of 2t is 2 cosine of 2t. And then the derivative of the component with our j vector is going to be negative 1/3 sine of t over 3. And there is our derivative vector for the vector-valued function r of t. All right. On to the next page. Here are some helpful rules for taking derivatives involving vector-valued functions. If u and v are differentiable vector-valued functions, and f is a differential real-value function of t, and k is a scalar, all these properties are true. We've got a scalar multiplication, kind of like our constant multiple rule for derivatives. The derivative of a constant times a vector-valued function is equal to the constant times the derivative of the vector-valued function, which of course we just saw the derivative of the vector-valued function is going to be another vector-valued function. We can write in component form. Sum and difference rule, the derivative of the sum of two vector-valued functions is the sum of their individual derivatives. Derivative of the difference of two vector-valued functions is the difference of their derivatives. And then we have product rules, both for multiplication by a real valued function and a vector-valued function, and for two vector-valued functions, where it behaves just like the product rule, but here we've got a real valued function times a vector, real valued function times a vector, both of which result in vector valued functions. We add those together, the result is again a vector valued function. And then here we've got the products of multiple vector valued functions. All right. Let's go ahead and look at example 5 here. Example 5 says, hey, let's find the unit tangent vector to the curve r of t equals cosine of t sine of t at t equals pi over 3. All right, so first thing I'm going to do is I'm going to find the derivative vector. R prime of t is going to be the component vector negative sine of t, comma cosine of t. And so now if we want to find the derivative vector at time pi over 3, we can just go ahead and substitute pi over 3 in here for t. And when we do this, this gives us the derivative vector, which the derivative vector may not necessarily be a unit vector, but it is definitely the tangent vector to the curve. Just like, it's the slope of a tangent line when we take the derivative of a real valued function. When we take the derivative of a vector valued function, it results in the tangent vector at that point to the curve. And so I'm going to go ahead and calculate these values. Sine of pi over 3 is root of 3 over 2. Cosine of pi over 3 is 1/2. And when I deliberately put unit vector in here so I could talk about this real quick. A unit vector is a vector with a length of 1. Okay, now when we have trig functions like this, this vector is going to have a length of 1 if we just have unitary trig functions because of the unit circle. But the length of this vector, if I take the magnitude of this and square this and add them together, I get a length of 1. That may not necessarily be the case. If I find a tangent vector and I want a unit tangent vector, all I need to do is take that tangent vector and divide it by its magnitude, and that'll give me a unit tangent vector in the same direction as my original tangent vector. Just a little extra piece to kind of think about there. All right. Example 6. Given the vector function r of t equals all this stuff, we're going to find the derivative and second derivative of this vector valued function. So first I'm going to go ahead and find the derivative, r prime of t, which is, again, it's a vector. If I take the derivative of this, I've got 1 over t squared plus 3t times the derivative of the inside. So the x component of the derivative vector is going to be 2t plus 3 over t squared plus 3t. And then the derivative of this, I've got a constant multiple 4, and then I'm going to apply the chain rule to this. So it's going to be 4 times the derivative of the exponent, which is 2t minus 2, times e to the t squared minus 2t. All right. And maybe I even want to simplify that second component a little bit. Make it a little bit easier for myself, I guess. And we'll make that just 8 times the quantity t minus 2 times e to the t squared minus 2t. So there's my first derivative. To get my second derivative, I need to take the derivatives of each of these components. And so I'm not just going to be able to write this down. I can't just take these derivatives right off the top of my head and write the second derivative down. So I'm going to have to go ahead and take the derivatives of those components and then write my second derivative in a moment. So let's take the derivative of 2t plus 3 over t squared plus 3t. I'm going to apply the quotient rule here. So we've got low times the derivative of high minus high times the derivative of low, square the bottom, and away we go. And if I expand this, that's 2t squared plus 6t minus 4t squared minus 12t minus 9. All of that over t squared plus 3t, quantity squared. And so that's going to be equal to, combine the like terms, negative 2t squared minus 6t minus 9, all over t squared plus 3t, quantity squared. So that's the derivative of that component. Then I'm going to take the derivative of the other component. And so I've got a constant multiple 8 out in front here. And then I've got the quantity t minus 2 times the derivative of e to the t squared minus 2t, which is going to be 2t minus 2. Wait a second. I forgot to factor it. I hope people were screaming at me there watching the video that I forgot to. That should be a t minus 1. Good thing I caught that at this point. Okay, so t minus 1 times 2 minus t times e to the t squared minus 2t plus e to the t squared minus 2t times the derivative of the quantity t minus 1, which is just 1. And so I can factor an e to the t squared minus 2t out of this. And what's left behind is 2 times the quantity t minus 1 quantity squared plus 1, which I guess I can simplify that. It's going to be 2t squared minus 4t plus 2 plus 1. So this ends up being 8e to the t squared minus 2t times the quantity 2t squared minus 4t plus 3. And so that's the y component of my derivative, of my second derivative. And so my second derivative vector is going to be, let's see, the x component was negative 2t squared minus 6t minus 9, all over the quantity t squared plus 3t, quantity squared. And my y component was 8e to the t squared minus 2t times the quantity 2t squared minus 4t plus 3. And there's our second derivative. And so there are our vectors that we wanted. R prime of t right here, and R double prime of t right there. All right, so pretty simple, straightforward. This was a bit of an ugly problem because we had some ugly functions as our components of our vector valued function, but we can overcome that. And basically, when we're trying to find the derivative and the second derivative of a vector valued function, take the derivative of the components. Boom, first derivative. Take the derivative of the components of that. Boom, second derivative. Pretty straightforward. All right, that brings us to the end of this video and this section. Join us next time when we move on to section 9.5 of AP Calculus BC, integrating vector valued functions. Coming up next. All right, have a great rest of your day, everybody. See you next time. Bye-bye.